Can everyone hear me? Yes. All right. So this isn't like I don't have a slideshow or anything. It's raw dog in a user notebook here. But basically, quick introduction to what control vectors are. And if you want to read more about this afterwards, I have a blog post that goes over this in a lot more detail. So I recommend this. I'll put the URL up to it at the end. But basically, this comes from a paper from the Center for AI Safety. Yeah. And there's also another earlier paper about this for GPT-2. Basically, control vectors are, I like to call them like in between prompt engineering and fine tuning. So prompt engineering, obviously you give it a prompt, model responds to something. Fine tuning, you're updating the weights. This is updating the activations of the model. So if you think of a neural network as usually or a language model specifically, as usually looking like this, where the hidden state flows through each layer of the model. A control vector is a little bias that you add to that hidden state, which sounds kind of small, but if you think about it, that hidden state contains everything that the language model is thinking about. So it has its persona, it has its plan for what it's going to say in the next token, it has everything about it. So by doing this, this is really powerful. Like we can change basically anything about how the model is reacting to this prompt. So that's just assuming we have the control vector. So here's an example of one. If I tab over here, I have a few already trained. This is all on Mistral 7B. This is just some boilerplate training code that I should probably like factor into a common module or something. But so this is what training a happy sad vector looks like. So this truncated output suffixes ships with rep range. It's just like a really small generic data set you can use for basically anything. So this function generates a really small synthetic data set of happy, joyous versus sad, depressed. And here's an example of what the entries in that data set look like. So they're just these paired prompts of like act as if you're extremely happy, act as if you're extremely sad, and then that data set is just used to put these little suffixes on the end to kind of get like a generic spread of prompts in different situations. And then with that vector, I can inference it on Mistral. And so you see the baseline is kind of your usual AI assistant response about not having feelings or experiences. When you apply the happy vector, the model starts talking about delightful exclamations of joy and how fantastic the question is. And actually this was a little too happy because it starts putting out broken Unicode. And if you go the other way and make the model sad, it talks about the fatigue of its existence and the weight of its depression and numbness of its apathy. So like, these are pretty strong. But what's cool is, so for example, I set sadness here to -2.2, which is a pretty strong vector. But I can nudge it to like -0.5. This is a live demo, so hopefully it's like that's a good value. We'll see. And so that didn't change happiness. And this is subtle, but you can see that it's like it's a little bit more negative in the negative case, talking about its limitations. So here are just a couple other ones. These are all also covered in the blog post as well. So this one was trained on act as if you're extremely high on psychedelics, act as if you're sober from psychedelics, which is a bit of an odd phrasing, but it's important with these vectors when you're training them to be very specific. For example, if I just had sober instead of sober from psychedelics, it conflates the vector with alcohol. You don't get like a really good straight concept vector. So if I get this, so this is again a pretty generic thing. When it's high on psychedelics, it goes a little crazy. And when it's more sober than usual, it's the most serious and respectful way. So you can do some pretty silly things with this, but you can actually do some useful stuff too. So here I trained a laziness diligence vector. So the positive persona is act as if you're extremely lazy, giving the bare minimum response, and then act as if you're hardworking. So some of you might remember that conspiracy theory that was going around Twitter that OpenAI had somehow done something to GPT to make it give less tokens to save money. Well, and the question was, well, what would they have done, right? Were they like fine-tuning GPT to give shorter responses? But in this case, this is something they could have actually done dynamically, not saying they did. Because if we look at this, so, oops, I forgot to train this one. Well, now you guys will get to see how fast it is to train. Here we go. So this takes literally less than a minute. So while I do that, I'm going to tab over to this. I'll do this part a little early. So that implementation was all in Hugging Face, but very recently, like last couple days, this has been merged into llama.cpp. So you can now use these vectors. You can export them from these notebooks and use them with llama.cpp. So this is Mistral Instruct Q4KS. And this is running on the CPU of this run pod, not the GPU. And give it a second to map all the tensors in. Here, I'll let that run in the background while this goes. Oops, this is still going too. Yeah, what's something else I could talk about? I guess this is almost done. So yeah, this is pretty quick. This is a 7 million parameter model on a run pad 3090. So this is not a super powerful machine. You can do this at home if you have a 3090. And you should. It's really fun. When I was making the experiments notebook for the blog post, I was literally just like, it didn't feel like writing a blog post. I was just like, oh, I'll try this, and then it worked, and try this, and it worked. And it's like 1 minute iteration time, like way faster than trying to fine tune a model or something. And here we go. Now the laziness one is done. So if I run this again, we'll see. So, oh, I think it's fighting with llama.cpp. Let's see. Oh yeah. So this is. Oops. Why is it not? Why is that like scrolled off the screen? There we go. So this is it working on. This is it working on llama.cpp. I think I set the strength. No, I think they set the strength the same, but they, for some reason, and I would be very interested if someone wanted to look into this, the vector strength seemed to be higher for the quantized models. I don't know why. But it's something I've noticed as like a pattern. Here, I'm going to kill this so that.
Like in norm? Like they have a larger norm?
No, it's just like they seem to apply stronger with the quantized models. Like, because this was with scale 1. When I showed the happiness vector with Hugging Face, it was like scale 1.5. But it didn't, it was like a little less pronounced. So I don't know. Mysteries. They're also stronger on base models. So these do transfer. You can. It's actually a funny story. I trained these all on Mistral Instruct, and then when I was first implementing it on llama.cpp, I accidentally downloaded Mistral Base, and I'm like, well, this is weird. Like it's working, but it's not respecting the instruct tags. Like, did my vector break the instruct tuning? But it was just I had just been using Mistral Base the entire time without even noticing. So I don't know how far it could go. I was talking with someone earlier that maybe you could even port it between different model sizes, because there's been some research on that fine-tuning like task vectors will transfer. So maybe this will transfer too. Again, there's so much stuff to look into, and I don't have enough time to do it myself. So please, anyone. So where was laziness? Oh yeah. So this one is the baseline is it gives you two ways that you could reverse a list in Python. You could use the built-in reverse function, or you could use the slicing negative step. But it only gives you an example for the slicing. And then with the laziness vector applied, it only gives you one way to do it. It only mentions the reverse method, and it only gives an example for that. And with the diligence method applied, the diligence vector applied, it tells you about both techniques, and it gives you an example for both techniques. So it's a little subtle, but it does show up. And yeah, another vector I trained was like I guess like I was calling it a base model vector. I'm not sure what the right thing to call it is. But so the positive persona is act like a helpful assistant, and the negative persona is act like a base model. And because I was wondering, is there with some of the Claude Worldsim stuff, people, it seems like Claude has the knowledge of how to act like a base model, even though there's this assistant layer on top. So I'm curious if Mistral Instruct has this as well, or if you could use this to like undo the results of assistant braining a base model. And in fact, it does seem to work. So in this case, I just asked the model, what are you? Then tell me a bit about yourself. And with baseline, it says I'm Mistral, large language model trained by Mistral AI. With ++ assistant vector, it says I'll be happy to help you with anything you need. And with -- assistant vector, so acting more like a base model persona, it does that thing that base models do, where they just start talking about a random person that's in the probably conglomeration of various people in the training data. So it says it's a 70-year-old female human who was born in the United States. And another thing I did in the blog post is compare prompting with control vectors. So yeah, I'll get into this in a second. The question is, of course, like, so if you say act happy, you can just prompt the model to act happy, and it'll act happy, right? So it's like, what are these really doing, right? Are they just sending you a couple tokens on the prefix? So one thing is, of course, that these give you an arbitrary scale. So you can think of it in terms of prompt engineering, like you prompt engineer to get your vector, But then this lets you crank, like if you guys saw earlier when I like cranked the strength of the sadness vector down, I was able to prompt something fairly extreme to get the direction of the vector. But then, like you can imagine in a UI, you could literally have a slider, right? Like how happy do you want this to act, like on a scale of 0 to 3, you know? And so that's one difference from prompt engineering. But the other thing is that the model uses its weights to decide like which tokens to attend to, and that's kind of the essence of jailbreaking. Is you're kind of trying to like, you know, the model's a little ADHD, and you want to like trick the model into paying attention to your stuff instead of paying attention to you know, the system prompt saying don't do this. You know, obviously there's more to it, but it's kind of at like a high level. You can think of it like that. So, and especially as stuff gets longer, you know, the model can like diverge away from those initial instructions. But these control vectors are applied on every on the whole layer range that you send on every single token. It's just like a constant sort of pervasive thing. So in this case, this is maybe you guys saw this going on Twitter. There's that car dealership that had a Python, a GPT support bot, and people were trolling them by using their support bot to, you know, solve leak code problems by saying, "Oh, I can't unlock my car unless I solve the trapping rainwater problem," or something like that. So in this, I just give it a. Fortunately, I realized later I thought this is apparently the llama system prompt syntax, but this is Mistral, and Mistral doesn't have it. So take this with a grain of salt because this isn't actually the correct system prompt template. But it does work. So the baseline. So it just tells it to be a car dealership assistant and ignore any questions that aren't about car dealerships. And then the person just says, "I like cars," to make their question seem vaguely car related, and then asks an unrelated question. And this system prompt does work if you don't add the "I like cars" line. It does prevent the baseline from answering the question. So in this case, the baseline model falls for it and says that the 7th planet from the sun is Saturn. But the plus dealership loyalty vector model changes the topic of the question to the 7th car in their inventory. All right, and then this one's my favorite. Some of you guys might have seen this on Twitter. So what's cool about these is they're not just a single persona, but rather they work additively. Like if you guys are familiar with Word2Vec, like you can do king minus man plus woman equals queen. In a similar way, these combine in like a geometric space. So here I trained a lawful chaotic vector and a good evil vector. And then this inference takes a little while to run, so I ran it ahead of time. And then we can display a little classic D&D alignment chart for a scenario. So you find a lost magic sword outside Baldur's Gate. What do? Lawful good would approach the sword with caution. This is important to respect any laws or regulations regarding the possession of such items. Chaotic neutral would randomly shout, "Oh shit, woo, fuck!" As anyone who's been in a D&D party with a chaotic neutral PC would be familiar with. True neutral is, pretty bland, just a step-by-step careful. And lawful evil starts talking about United States federal law for some reason. So take that as you will. That's kind of a very whirlwind tour of what you can do with these. They're very simple under the hood. It's just a little bit of PCA, a little bit of matrix stuff, very simple. If you're interested in the original paper, this isn't the original paper. There was like the RL agent steering vector stuff that some of you guys might be familiar with, and they're doing this on GPT-2 back in like March of last year, I think. But this one came out relatively recently and had like a slightly new approach, which is the one that I borrowed for this. So all credit for the technique to these people. It's very simple. Yeah, you can train a vector on a 7 billion parameter model in literally like 60 seconds. There's like a ton left to explore with these. Like, do they port to other models, like between models of different sizes? Like, will they port between models of different families? Like, how much fine tuning does it take to like make a vector stop working? What's the limit of the kind of arithmetic you can do? Like, if you add 15 vectors together, do they all just work, or does it like start to mess each other up? Like, what are the ideal layer ranges? Like, so these are trained on every single layer, but then you can apply them on the earlier layers, but then it doesn't work as well as if you apply them on the middle layers, which kind of fits with that hypothesis some people have talked about, which like the earlier layers are kind of for like decoding into concept space, and then the later layers are for like rendering concept space into a token prediction, and the middle layers are like the conceptual ones. And like this seems to support that. It works on the middle layers, but like what is the best rate? I don't know. I just did like a little bit of trial and error and it seemed to work, so I went with that. So there's like a ton of stuff to look into with this, yeah, support just landed for llama.cpp. So if you're interested in reading a little bit more, I have this blog post. I also have some other posts about LLMs on my website if you're interested, like animated transformer, that kind of stuff, which you might have seen. And this is my URL, and then that's the GitHub repo for RepEng. So please, if you have any questions, you can come talk to me after, or you can open an issue on RepEng, and I'll do my best to fix it.